Okay, here we go. All right, so these are the objectives for this section here. First of all, what is a rational number? Well, ladies and gentlemen, there's actually two definitions for a rational number, but they're really synonymous with one another. One definition is to say that any number that can be expressed as a fraction is called a rational number. So any number that can be expressed as a fraction, whether it's a proper or improper fraction, or even if it's a mixed number, it's still called a rational number. All right. Ladies and gentlemen, an integer is a rational number. If you give me any integer, I don't care what the integer is, like -2 is a rational number because I can express -2 as a fraction. By simply placing -2 over 1, I have expressed it as a fraction. That's why we call this a rational number. All integers are rational numbers, but now not all rational numbers are integers. For instance, 5/6 is a rational number, but it's not an integer. Okay, it's not an integer. Now, the top number of our fraction is called the numerator, and the bottom number of our fraction is called the denominator. An easy way to remember this is just to remember that the denominator is always in the downstairs. So D stands for downstairs, okay, in the basement. So numerator's on top, denominator's in the basement or downstairs. It's in the bottom of the fraction. Fractions or rational numbers can always be called also ratios, all right? A ratio is a comparison of two numbers, and ratios are often written as fractions. And so therefore ratios and rational numbers are basically one and the same, all right? Okay. Now, all of the integers that we've touched base with in the past are also rational numbers. And in fact, I want to show you this right now, the relationship between all the numbers that we'll work with in this course here. This overall set here is called the set of real numbers. We can partition the set of real numbers up into two smaller subsets. A subset consisting of rational numbers and a subset consisting of irrational numbers. A smaller subset inside the set of rational numbers is called the set of integers. A smaller subset embedded inside the set of integers is called the set of whole numbers. A smaller subset embedded inside the set of whole numbers is called the set of natural numbers or counting numbers. So every natural number is a whole number, and every whole number is an integer, and every integer is a rational number, and every rational number is a real number. Not necessarily is it true that every rational number is an integer. 2/3 is a rational number, but it's not an integer. It's not true that all integers are whole numbers. For instance, -3 is an integer, but it's not a whole number. It's not necessarily true that all whole numbers are natural numbers, because 0 is a whole number, but it's not in a set of natural or counting numbers. Okay. If a number is not rational, then it is irrational. And there's an infinite number of irrational numbers. A couple of them would be pi. Pi is an irrational number. It pertains to the ratio of the circumference of a circle to its diameter. Pi's decimal is approximately equivalent to about 3.14. But in reality, this decimal rambles on and on and on, never terminating or never repeating. I believe, I think it was Japan, they took pi out to 20 trillion decimal places on a computer, and it still showed no signs of termination or repeating. Safe to say that pi is probably irrational. The square root of 2 is an irrational number. The square root of 7 is an irrational number. In fact, ladies, on the square root of any prime number is an irrational number. So there's an infinite number of prime numbers. There's an infinite number of rational numbers. Base E, which is called a natural base in mathematics, which is approximately about 2.718, is an irrational number because its decimal rambles on and on, never terminating or never repeating. So there's an infinite number of rational numbers, and there's also an infinite number of irrational numbers. Either way, they're always real numbers, okay? There is a larger set of numbers that does engulf the set of real numbers, of which we're not going to get to in this course. It's called the set of complex numbers. So every real number is a complex number, but not necessarily is it true that every complex number is a real number. And so this kind of gives you a bird's eye view, ladies and gentlemen, as to the hierarchy of the sets and the relationship to each other by using this Venn diagram here, okay? All right. All right. So I indicated that every integer is a rational number in the sense that we can always place it over 1 and express it as a fraction, okay? Now, so where are the location of all these numbers on a number line? Well, 2/3 would be between 0 and 1 on a number line, all right? And just for the record, how many fractions or rational numbers exist between any two integers on a number line? In other words, how many fractions are there between 0 and 1? Well, you got 2/3. You would also have what? 1/2, 3/4, 1/4, 1/10, 1/100th, 1,000th, 1,000,000th, 1,000,000,000th, 1 gazillionth. There's an infinite number of fractions or rational numbers between any two integers on a number line. An infinite number of them. Can't even count them all, there's too many. A continual swath of fractions between 0 and 1. Infinite number. All right. Okay, let's move on here. All right. When the numerator of a fraction has a smaller absolute value than the denominator, basically, when the numerator is smaller than the denominator, we call the fraction a proper fraction. So an example of a proper fraction would be like 2/3, because the numerator is less than the denominator. 10/11ths would be a proper fraction. 99/101 would be a proper fraction. Okay. If, however, ladies and gentlemen, the numerator is greater than or equal to the denominator, then we call the fraction an improper fraction. So a -11/2 would be an improper fraction because 11 is greater than 2. That's an improper fraction. 9/9 is an improper fraction because the numerator is equal to the denominator. All right, 101/99 would be an improper fraction. All right. -15/8 would be an improper fraction. Okay. A mixed number is a number that possesses a whole part and a proper fractional part. For instance, 3 1/2 is called a mixed number. The whole part of the mixed number is the 3. That's the whole part of the mixed number. And the proper fractional part of the mixed number would be 1/2. That's the fractional part. This is called a mixed number. All right. And 3 1/2 is equal to 3 plus 1/2, by the way. That's called a mixed number. All right, now, oftentimes it's necessary to navigate back and forth between an improper fraction and its equivalent mixed number form. So like 17/6, how would I write 17/6 as an equivalent mixed number? Well, to do so, all we have to do is divide the denominator into the numerator. So we're going to divide 6 into 17, okay? And so as I'm dividing 6 into 17, 6 divides into 17 2 times with 5 left over. Therefore, 17/6 is equal to, what's the whole part? 2 whole, and the fractional part is 5/6. All right, so 17/6 is equivalent to 2 5/6. 2 and 5/6. Do you see it? Okay. So 17/6 is equal to 2 5/6. 17/6 is equal to 2 5/6. 2 and 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 5/6. All right, let's go backwards. Suppose you want to write 7 2/5 as an improper fraction. Well, to go backwards is pretty simple. All we do is we're going to take the whole part, which is 7, multiply it by the denominator, which is 5, and then we're going to add the numerator to that, which gives us 37. And so therefore 7 2/5 is going to be 37 over 5. Again, how did we get that? We took 7 times the 5 down here, 7 times the 5, and then we added to that the numerator 2, and we place this all over the denominator of the proper fraction, 37/5. If you were to go backwards and change 37/5 back into a mixed number, how many whole times does 5 divide into 37? 7 whole times, with what left over? 2/5. So 7 whole times and 2/5. 7 2/5. Do we understand how we're going back and forth between mixed numbers and improper fractions?
Yeah, makes sense.
All right. Now, since fractions can be thought of as a division of two integers, we can make use of the rules for division of signed numbers to address the sign of a fraction. Bottom line, ladies and gentlemen, is what they're trying to get at here is if you have a negative fraction, it doesn't matter where you attach the negative sign. For instance, if you have a negative rational number, negative 3/5, you could attach the negative sign to the numerator and call it negative 3 over positive 5. Or you could just as well attach the negative sign to the denominator and call it positive 3 over negative 5. These are all equivalent to each other. Make sense? They're all equal to each other. No difference between them. So that's something to keep in mind for any negative fraction. Doesn't matter where you attach the negative sign. All right. Now, what does it mean for a fraction to be reduced, or in simplest or lowest terms? Ladies and gentlemen, it means that if I have a fraction in reduced or simplest terms, the only common divisor between the numerator and denominator would have to be 1. So if 1 is the only number that divides into both the numerator and denominator of a fraction, we say that the fraction is in reduced form or in lowest terms or in simplest form, okay? If, however, the numerator and denominator can be divided by some other number than 1, then the fraction is not in reduced or form or lowest term or simplest form. For instance, 4/8 can be further reduced because 4 divides into both the numerator and the denominator. So dividing 4 into both the numerator and denominator, we can reduce 4/8 down to an equivalent fraction called 1/2. All right. So therefore, we say that 4/8 is equal to 1/2. You see, because we really took 4/8 and we really divided it by what? 1. Isn't 4 over 4 another name for 1? So ladies and gentlemen, when you divide a number by 1, you still have the same number. That's why 4/8 divided by 1 in the form of 4 over 4 is really still the same number. It looks different, but it's still equivalent to 4/8. It's 1/2. All right. Any questions about that there? Now, since you can use a calculator in this course, reducing fractions is really not going to be that strenuous, because you can speed up things on the calculator to try to find the common divisor between the numerator and the denominator. All right, ladies and gentlemen, so here's classwork number 1. See if you can reduce these fractions into lowest terms or simplest form, okay? Go ahead, you can use your calculator, whatever resources you got. Let's try to get these reduced down to simplest form. Classwork number 1. All right, one way to reduce 18/24 is kind of like the direct way. And I think of a number that divides into both 18 and 24, and obviously the larger number you can think of, the quicker you're going to get this thing in reduced form. Ideally, we're searching for the greatest common divisor of 18 and 24, the largest number that divides into both 18 and 24. But suppose you can't think of that. Well, I'll just start off with any number. How about 2? Both numbers are even, so therefore 2 must divide into both 18 and 24. So let's just start to chip away at this by reducing the top and bottom down by 2. When we do that, we get it down to 9 over what? 12. Can 9/12 be further reduced down? Well, after a little thought or playing around with the calculator a little bit, we discover that 3 divides into both 9 and 12. And so this can be further reduced down by 3, down to 3/4. And notice the only common divisor that 3 and 4 have now is 1. Because of that, we call this reduced or in simplest form. That's your answer. You cannot reduce it anymore. 8/21. The only numbers that divide into 8 would be like 2, 4, and 8, but none of those divide into 21. Because of that, les amis, this cannot be reduced. Because the only common factor between 8 and 21 is 1. That's why we call this reduced or in simplest form. Now, another way you could have divided those fractions is to use the prime factorization method. It's a little bit more drawn out, but it always pays the bills. Take 8 and write it in prime factored form. So you can build an upside down prime factorization tree. A prime number is a number divisible only by 1 in itself that's greater than 1. It's a whole number greater than 1 that's only divisible by 1 in itself. 2 times 4 is 8. 2 is prime, circle it. 4 factors down into 2 times 2, both of which are prime. So the prime factorization of 8 is 2 times 2 times 2. 24. Let's find the prime factorization of 24. 3 times 8 gets us started. 3 is a prime number, circle it. 8 further factors down into 2 times 4. 2 is prime, circle it. 4 further factors down into 2 times 2, both of which are prime. Therefore, the prime factorization of 24 is 2 times 2 times 2 times 3. Now that you have both the numerator and denominator torn completely apart into their prime factorizations, it's easy to see what factors drop out or cancel or reduce out. This 2 reduces out with this 2. This 2 reduces out with this 2. This 2 reduces out with this 2. When you reduce these out, you leave behind factors of 1. So what we have left in the numerator is just 1. In the denominator, the only thing that survives is 3, 1/3. Oh, I'm sorry. That was supposed to be 18/24. Well, I did a different problem. Okay, but the way to reduce 8/24 is to reduce it down to 1/3 by using the prime factorization method. Suppose you didn't want to take that route. You want to use the more direct route. Can you think of a number other than 1 that divides into 8 and 24? The quickest way to get there is to think of 8 itself. 8 is the greatest common divisor of 8 and 24, and immediately it takes it down to 1/3. Suppose you can't see that or think about that. Well, then start chipping away at this. Maybe start dividing the top and bottom down by 2. Take it down to 4/12, and then reduce the top and bottom down by 2 again. Take it down to 2/6, and then maybe reduce the top and bottom down again by 2. Take it down to 1/3. Either way, you cut it, slice it, or dice it, ladies and gentlemen, we're going to get down to 1/3 if we do things correctly. Okay? All right, so there's different ways in which you can factor these fractions down. You feel free to always tear the numerator and denominator down into their prime factored form, and then you can easily see what drops out to do it that way. Some people don't like to mess around with this. It is a little bit more drawn out, I will say. This is the more direct way of taking care of business, and this is the directest way, if you can, for this problem. You cannot reduce this any quicker than this way right here. Because ideally, to reduce a fraction down the quickest, you want to get the greatest common factor or divisor of the numerator and the denominator. That takes it down the fastest. Okay. All right. Let's move on. All right, this is just showing you ways of reducing those fractions down. Other ways it might have deviated slightly from our way. Bottom line is we get the same reduced fraction. Okay, and 8/21 cannot be reduced. All right, let's go in reverse direction now. Instead of reducing a fraction, can we build a fraction up into what's called an equivalent fraction? The answer is yes. If you're given a fraction a over b, whether it's proper or improper, doesn't matter. If you multiply both the numerator and the denominator by the same number, you will always crank out an equivalent fraction of the original fraction. So the fraction AC over BC is equivalent to A over B. All right. So 1/2. How many equivalent fractions does 1/2 have? Well, I could multiply the top and bottom of this fraction by 2 to build it up to 2 over 4, which is equivalent to 1/2. Or I could have multiplied the top and bottom of 1/2 by 3, which would build it up to 3 over 6. 3/6 is equivalent to 1/2, also equivalent to 2/4. Or I could have multiplied the top and bottom of this fraction by 4 over 4 to build it up to 4 over 8. 4/8 is equivalent to 1/2, also equivalent to 3/6, equal also to 2/4. Or I could have multiplied the top and bottom of this thing by 5 and build it up to an equivalent fraction of 5/10, which is equal to all these other fractions. Ladies and gentlemen, how many equivalent fractions does 1/2 have?
Infinite.
What do you think? There's an infinite number. You could go on to the end of time or death, whatever grabs you first, in enumerating equivalent fractions of 1/2. There's an infinite number of representations of 1/2. And that goes for any fraction. There's an infinite number of equivalent fractions to any fraction. Infinite number. Okay. And that goes for negative fractions too. All right, let's do this problem here. 3/8 would be equivalent to what fraction over 32? Well, ask yourself, what did they multiply this 8 by to build it up to 32?
4.
4. That means you got to multiply the numerator by 4 also. So what's 3 times 4?
12.
So 12 over 32 is an equivalent fraction to 3/8. They're equal to each other. 5/4 builds up to what equivalent fraction with the denominator of 56? What did they multiply 4 by to build it up to 56?
14.
You got to multiply the numerator by 14 then. So what's 5 times 14?
70.
So 70 over 56 is equivalent to 5/4. Those are equivalent fractions. Or we say 70 over 56 reduces back down to 5/4. Or 12 over 32 reduces back down to 3/8. They're equal fractions. They have the same location on the number line. Bless you.
Thank you.
All right. All right, how do we multiply fractions together? Well, this is basically the prototype for multiplying two fractions together. Notice when we multiply fractions together, do we have to have a common denominator?
Yes. Oh, we don't.
We do not need a common denominator when we multiply fractions. Don't need one. So, ladies and gentlemen, how do we multiply fractions together? Well, we multiply the numerators together and place that product over the product of the denominator. And then, of course, we always try to do what, if possible, in the end? What do we always try to do?
Reduce the fraction.
Reduce. Always reduce your fractions. So we'll try to reduce, if possible, in the end. If you can't reduce it, leave it alone. But if you can reduce it, let's try to reduce it. Okay? All right, so in general, that shows us how we multiply fractions together. Notice the denominators are not the same here, and they don't have to be the same. So please don't try to get common denominators when you're trying to multiply fractions together. You don't need them. All right, so 5/3 times 5/8, excuse me, times 3/5. How do we do it? Well, we can multiply our numerators together. So we got 5 times 3, and that sits over 8 times 5. And that nets me 15 over 40. But can this be reduced?
3/8.
You know, like, I mean, any number that ends in a 0 or a 5 is divisible by 5. That's called the 5's divisibility test. I'll try to post those divisibility tests on Canvas so you can look at them. So I know this is reducible at least by 5, if nothing else. So this takes us down immediately to 3/8, and we cannot reduce this anymore, 3/8. All right, that makes sense? You know what, ladies and gentlemen, there's another way to do this problem. I'm gonna show it to you. And I'm gonna let you decide. Has anybody in here ever heard of cross canceling?
Yes.
It's legal. You can do it. Now watch this. Cross canceling speeds up your reduction. If you don't cross cancel, sometimes you're gonna have big numbers in the end to try to reduce. Cross canceling nips it in the bud. Look at, we can cross cancel between these 5s here. We say 5 divides into itself one time. 5 divides into this 5 down here one time. That's called cross canceling or cross reducing. It is a legal thing to do. Notice we cannot cross cancel or cross reduce between the 3 and the 8, because the only thing that divides into 3 and 8 is 1. What do we have left in our numerator? 1 times 3 over what do we got left in our denominator? 8 times 1. Do you agree? We got it down to what? 3/8? Everybody see that there? Same answer, just a different way of going about it. All right, -5/9 times 3/11. Ladies and gentlemen, what's a negative times a positive?
A negative.
Gonna be a negative. And then you can do it this way if you want. 5 times 3. Place that over the product of the denominator. 9 times 11. In which case this is going to be now -15 over what, 99? Can we reduce this down?
Yes.
I know 3 will at least divide into both 15 and 99. And then when we reduce down by 3, we take it down to -5 over what, 33? Can we reduce -5 over 33?
No.
No, that is reduced. Another way to do the problem. Suppose you're in the cross canceling. So another way we could have done this problem is this way. Notice we cannot do any cross canceling between the 5 and the 11. However, can we do cross canceling between the 9 and the 3?
Yes.
The answer is yes. 3 divides into itself one time. 3 divides into 9 3 times. What do we have left? Negative what? 5 times 1 in the numerator, which is -5. And in the denominator, we got 3 times 11, which is what? 33. Same answer. So if you're in the cross canceling, it does speed things up and it stays off having to reduce potentially large numbers in the end. That's the nice thing about cross canceling. If you don't want to do cross canceling, well, just have your calculator handy. You may need it to reduce some big numbers in the end. Bottom line is, I don't care what method you choose. The bottom line is we got to get correct answers. All right, ladies and gentlemen, how do we multiply 1 3/4 by 2 2/5? Multiplying these two mixed numbers together. First, we have to turn them into improper fractions. So how do I turn 1 3/4 into its equivalent improper fractional form? I take 1 times 4, which is what?
4, then you add.
And 4 plus the numerator 3 gives me what? 7 over what? 4. 7/4 is equivalent to 1 3/4 times, let's turn 1 2/5, or excuse me, 2 2/5 into its improper fractional form. I take the whole part and multiply it by the denominator. 2 times 5 is 10. Then I add the numerator to 10 to give me 12. And I place the 12 over the denominator of the fractional part. 12/5 is equal to 2 2/5. Now we just have to multiply. Now if you don't cross cancel, you're going to be left with 7 times 12, which is 84, big number. And then 4 times 5 is 20. Can we reduce? And can you think of maybe the largest number that divides into both 84 and 20? The largest. You can chip away at it with 2 if you want. It's going to take a little longer, but you'll get there. Do we think of something bigger than 2 that goes into both 84 and 20, though?
12.
12 don't divide into 20.
Oh.
4.
4.
6.
6 don't divide into 20. How about 4? Better than 2. 4 goes in 84, what? 21 times. 4 divides into 25 times. Can we further reduce this?
No,
4 and 1/5.
Yeah.
Yeah, but it is reduced though. It is a reduced fraction because 1 is the only thing that divides into 21 and 5. Granted, it's an improper fraction. Now, I don't care if you leave improper fractions as improper fractions as long as they're reduced. If you want to turn this into a mixed number, you're going to have to find out how many times 5 divides into 21. So 5 divides into 21, how many whole times?
4,
4 whole times with what left over?
1.
1/5 left over. So this would be 4 and 1/5. But again, I don't mind if you just leave it as 21/5. Make sure you read the instructions carefully with Alex because they may indicate what form they want your final answer to be in. Okay, and that's one way to do this problem, 21/5 or 4 and 1/5. Another way to do this problem is to do cross canceling. Can I cross cancel between the 5 and the 7? The answer is absolutely not. How about the 4 and the 12? Anything divided into 4 and 12?
2.
4,
2 will, but ladies and gentlemen, can we go bigger than 2?
4,
How about 4 itself? 4 divides into itself 1 time. 4 divides into 12 up here 3 times. 4 divides, into here 3 times. So what am I left with? 7 times 3 is what? 21. And 1 times 5 is 5. We get the same answer regardless of how you decide to do the problem, okay? But whether you're in the cross canceling or not, ladies and gentlemen, if you do things correctly, you will get the correct answer in the end anyways. Any question about any of these problems on here? All right, how do we divide fractions? Well, in order to divide fractions, we have to understand how to take the reciprocal of a fraction. And so we say that when you have a fraction a over b and you flip it upside down to get a fraction b over a, these are called reciprocals of each other. So a over b is a reciprocal of b over a and vice versa. Or sometimes they're more fancily called multiplicative inverses. Okay. So reciprocals are also multiplicative inverses. The reason why they call them multiplicative inverses is because if you multiply reciprocals together, you always get a product of 1. That's why they're called multiplicative inverses. You're always going to get a product of 1 when you multiply reciprocals together. Okay. All right. How do we divide fractions? Here it is. Here's the prototype. When you divide a fraction a over b by a fraction c over d, you change division to multiplication. And then you flip the second fraction upside down. So dividing by a fraction is like multiplying by a reciprocal. So dividing by c over d is like multiplying by d over c. Don't forget to flip the second fraction upside down. Never flip the first fraction upside down. Only the fraction that follows the division sign. And then you're back to multiplication. So you can either multiply across and then reduce, or do cross canceling first, then multiply. Any questions about this? All right, so let's try a couple out here. How about 3/4 divided by -5/8? Keep the first fraction the same. Change division to what? Multiplication. Flip the second fraction upside down. What's the reciprocal of -5/8?
8/5.
8/5.
All right, you fell into a common trap. Some of you think when you take the reciprocal of a fraction, it changes the sign of a fraction. It does not. So if you have a negative fraction, the reciprocal is still negative. If you have a positive fraction, the reciprocal is still positive. Still going to be negative, but it'll be -8/5.
So always keep the sign no matter.
Yep. Don't change the sign when you reciprocate a fraction.
I didn't realize you were referring to the like the negative too. I just thought you meant like the switch of the fraction.
Okay. What's a positive times a negative?
A negative.
Negative. If you're in the cross canceling, be my guess. If you're not in the cross canceling, what's 3 times 8? 24?
4,
What's 4 times 5?
20.
Can we reduce this?
Yes, we can.
Give me the largest number you can think of that divides into both 20 and 24.
4.
4. You could use 2, but it's going to take longer with 2 to reduce this down. 4 will get it reduced down quicker. Preferably, you're always searching for the greatest common divisor, both the denominator and the numerator. So this reduces down to what? -6/5? And I don't think we can go down any lower than that. That's reduced. Leave it like that. You don't need to turn that into a mixed number. If you insisted on a mixed number, you would say -1 1/5. Okay. But you can leave it as -6/5. Unless the instructions indicate explicitly that they want it as a mixed number. All right, so always read your instructions carefully with Alex. If they don't specify one form or another, I guess it should be, both forms should be accepted as an answer. And if it's not, if they complain about it and they did not specifically indicate the instructions, take a screenshot, send it to me, I'll investigate. All right, ladies and gentlemen, you do this problem here. We'll add this on the classwork number 1. 11 halves divided by 4 ninths. Go ahead and do that problem. Classwork 1 still. All right, so we change multiplication division and flip only the second fraction upside down, not the first fraction. There is no cross canceling available either way between 11 and a 4 or the 2 and a 9, so we multiply across. 11 times 9 is 99. 2 times 4 is 8. That is reduced. The only thing that divides into both 99 and 8 is 1. It is an improper fraction, but it is reduced. I mean, you don't have to turn that into a mixed number. Suppose that you insisted that it be turned into a mixed number. Well, you got a little more work to do. 8 divides into 9 1 time. 8 divides into 19 2 times. Remainder 3. Hence 12 3/8 would be the equivalent mixed number form for 99/8. 12 3/8. Okay. 12 3/8. Anybody get that?
Yes,
Yeah, I did.
I did.
All right, now adding and subtracting fractions, ladies and gentlemen. This is so important that I am going to actually take time, burn valuable time to write this out. We always need a common denominator when we add or subtract fractions. Okay. Do you need a common denominator when you multiply or divide fractions?
No,
No, you do not. Don't waste your time finding them. Do we need a least common denominator when we add or subtract fractions or mixed numbers? Answer is
yes,
yes. Must have one. If you don't have one, you're doing illegal math. Okay. Gotta have a common denominator whenever you add or subtract fractions. All right. So why is life good with these problems?
Cause they both
It's
have,
already a common denominator.
Already have a common denominator. So therefore, 5 12s plus 11 12s. I'm about to make a critical mistake because I've seen this garbage before in the past. Oh yeah, I've actually seen this before. Don't let this happen to you. This is not correct. Ladies and gentlemen, when you add fractions together that have a common denominator, you only add the what's together,
the numerator.
only the numerator. You do not add the denominators together. You place the sum of the numerator over the common denominator, and then you try to reduce. You don't do this, all right? I've seen this before. Don't do that. Oh, you can do anything you want. It doesn't mean it's correct mathematically. All right. So what is the sum of these two fractions since they possess a common denominator? It's going to be 5 plus 11 over 12. And what does that give us? 16 12s. Can I reduce 16 12s? Can you possibly give me the greatest common divisor of 16 and 12?
Will be 4.
4.
4. 2 would work. You can nibble away with it at 2. It's going to take longer, but 4 gets us there quicker. So therefore, this reduces immediately down to 4/3. Or if you insist in turning this improper fraction into a mixed number, it'd be 1 1/3. How about 7/3 minus 4/3? Got a common denominator, so I just subtract my numerators. Don't subtract your denominators. So it's going to be 3/3, and 3/3 reduces down to what?
1.
1.
1 whole. That's just another of an infinite number of ways of representing 1, 3/3. Okay. Any questions about those problems? Those were easy ones because you already had a common denominator. But you know where this is going, don't you?
Yep.
What if we don't have a common denominator? Well, then we have to get one. Okay. All right. So adding and subtracting fractions with different denominators. Step number 1. First, we have to find the least common multiple of the denominators. This is usually called also the least common denominator. So whether you call it least common multiple or least common denominator, those are the same numbers. Step 2, we then need to rewrite each fraction as an equivalent fraction. Equivalent fraction with the denominator equal to the least common denominator. And once we then build our fractions up into equivalent fractions that both possess the common denominator, we just add or subtract our numerators and place our result over the common denominator and then try to reduce in the end. Okay, try to reduce in the end. Now, the biggest challenge, one of the largest challenges of this procedure is trying to come up with that darn least common denominator of 2 or more denominators. Unfortunately, maybe a little less of a challenge, but still a challenge, is then building your fractions up to equivalent fractions. Once you accomplish steps 1 and 2, step 3 is like, it's like playtime then. Okay. All right, find each sum or difference. Okay. Now, normally, ladies and gentlemen, we can look at the denominators and determine what the least common denominator is. We can normally do that visually, but sometimes we cannot do that visually. In which case we may have to resort to another technique. But 1/4 plus 1/6, this one is pretty simple to determine the least common multiple or denominator of 4 and 6. So what is the smallest number that is divisible by 4 and 6? What's the smallest number that 4 and 6 divide into?
2.
No, 2 is a common divisor of
24.
6. I need a common multiple of 4 and
Oh,
6.
Oh, 12. 12.
Okay, 12. You see, these are common multiples of 4. 4, 8, 12, 16, 20, 20 what? 4, do you agree? These are common multiples of 4, and of course, there's an infinite number of them. Common multiples of 6 would be 6, 12, 18, 24, 30, etc., etc., etc. Now, ladies and gentlemen, check this out. Notice 24 is a common multiple between 4 and 6, but is it the least common multiple?
No.
Not the least. We
Okay.
can go smaller than 24. 12 is called the least. That is the least common multiple or the least common denominator of 4 and 6. Okay? That's the least common multiple or the least common denominator. All righty. Now, suppose you're having a hard time visually just looking at 4 and 6 and determining what the least common multiple is. It happens. And there might be problems where our denominators are bigger, where it might become a serious problem. This one, normally most people can see and reason that 12 is the least common multiple of 4 and 6. But suppose you can't. I have 2 other ways I want to show you how to find the least common multiple of 4 and 6. And I'm going to let you decide what you're going to do in the future. Okay? But I'm going to show you, ladies and gentlemen, 2 other ways to find the least common multiple of 4 and 6. Both these methods work. All right. Here's a method called the repeated division by prime method. Repeated division by prime method. You put 4 and 6 in kind of like an upside down division bar. Everybody see that there? Okay. Now, can anybody give me a prime number that divides into at least one of these numbers? It has to divide into at least 4 and or 6. It has to be a prime number, though. Oh, but what's a prime number? Oh, no. If we don't know what a prime number is, this is dead on arrival. Ladies and gentlemen, a prime number. What is a prime number? A prime number is a whole number greater than 1. So 1 is not a prime number. That is divisible by only 1 and itself. I'm going to list the first several prime numbers. 2 is a prime number because the only things that divide into 2 are 1 and 2 itself. 3 is a prime number because the only divisors of 3 are 1 and 3 itself. Is 4 a prime number? 4 is not prime because in addition to being divisible by 1 and 4, 4 is also divisible by what? By 2. 4 is not prime. Is 5 a prime number?
Yes.
5 is prime. Is 6 a prime number?
No.
No. 6 is divisible by 2 and 3 in addition to 1 in itself. Is 7 prime?
Yes.
7
Yes.
is prime. Is 8 prime?
No.
No.
No. Is 9 prime?
No.
No. Don't think all odd numbers are prime. 9's an odd number, but it's not prime. 9 is divisible by 3 in addition to 1 in itself. Is 10 prime?
No.
No. Is 11 prime?
Yes.
Yes.
12 prime?
No.
No.
12 is divisible by 1, 2, 3, 4, 6, and 12. Do you agree? 12 certainly not prime. Is 13 prime?
Yes.
Yes, 13 is a prime number. Is 14 a prime number?
No.
No, it is not. 14 is divisible by 2 and 7, and in addition to 1 and 14. Is 15 prime?
No.
No. 16 prime?
No.
I got a question for you. Do you think we're ever going to have any other even numbers that are prime listed here? Why can I not have any other even number as being a prime number in this list other than this guy? Because any other even number is always divisible by what?
Two.
By 2. By 2. 2 is the only even prime number that exists. That's it. All right, so 14 might as well throw out all the other even numbers. 15 is not prime, 16 not prime, 17 prime,
Yes.
18 is not prime, it's even. 19 prime,
Yep.
yes. 20 is not prime, 21 prime,
No.
no. 21 is divisible by 3 and 7. Is 22 prime? Absolutely not, it's even. 23 prime, yes. 24 prime, no. 25 prime, 25 prime,
No.
26 prime, no. 27 prime. Is 27 prime?
No.
No. 3 and 9 divided into 27. Is 28 prime? No. 29 prime.
Yes.
29 is prime. I got a question for you. How many prime numbers do you think exist?
Infinity. There's a lot.
Yeah, there's an infinite number of prime numbers, Lizum, and that can be proven in a proof course in mathematics. There's an infinite number of prime numbers. Believe it or not, very large prime numbers are used in the real world for data encryption. How many people ever bought anything online? Well, I got my hand up. Well, when you send your critical card, credit card information or debit card information and maybe other critical information, first the information gets encrypted, and they use large, very large prime numbers to do data encryption and data decoding in computer science, okay? So prime numbers are actually used in the real world, ladies and gentlemen. All right, how did I get on this? Can anybody give me a prime number that divides into at least 4 and or 6?
2.
2. 2 divides into 4, 2 times. 2 divides into 6, 3 times. Can you give me a prime number that divides into at least one of these numbers? At least one of them. It has to divide into one of them. Doesn't have to divide into both of them necessarily, but it has to divide into at least one of them.
1.
1's not a prime number.
Oh my.
2.
2. 2 divides into itself once and does not divide into 3 evenly. We just bring the 3 down. Can you give me a prime number that divides into 3?
3.
3 itself. 3 does not divide into 1, divides into itself 1. Ladies and gentlemen, when we get nothing but 1s down here, we are done. Now, what have I accomplished? My least common multiple, or the least common denominator of 4 and 6, is the product of these prime factors. 2 times 2 times 3, which is what? 12. Everybody see that method? That's called repeated division by prime method for finding the least common multiple of 2, or you could have more than 2 numbers. You could have 3 or 4 or any number of numbers in here. This method works for any number of numbers for finding the least common denominator or multiple of them. It's called a repeated division by prime method. Anybody ever see that method? It always works. Okay, here's another way. Here's another way we could have found the least common multiple of 4 and 6. It's called the prime factorization method. This is called the prime factorization method. This method also works. As the name suggests, we're going to have to take both these numbers and tear them down into their prime factored form. I like to use these trees. 2 times 2 is 4, and both 2's are what? Prime. We're done. We have nothing but leaves in our tree. No more branches are coming out of leaves. So the prime factorization of 4 is 2 times 2. What's the prime factorization of 6? 2 times 3, both of which are what? Prime. That's the end of that prime factorization tree. 2 times 3 is the prime factorization of 6. Now, ladies and gentlemen, we can put together the least common multiple of these 2 numbers. To do so, we must always choose the greatest number of factors between both factorizations. So, what's the greatest number of 2's? The greatest 2's between the 2 factorizations. How many 2's are in this factorization? There's 2 of them. How many are in this one? There's only 1 of them. What's the greater occurrence? 2 2's or 1 2? 2 2's or 1 2?
2 2s.
You got to have 2 2's in your least common multiple. Now, 3. Notice there's no 3s in this factorization, but there is one 3 that appears here. So what's the greater occurrence of 3? No 3s, 0 3s, or 1 3? 1 3. Got to have 1 3 in your least common multiple. And guess what number we get? We get 12. So I'm going to put together least common multiple. You always need the greatest 2s and 3s in this case between the two different factorizations. The greatest occurrence of the 2s is 2, not 1. You don't say 3 2s because you don't join these factorizations together and count totally 3 2s. It's between the separate factorizations. What's the greatest occurrence of 2? Here it occurs twice. Here it only occurs once. Only 2 2s occur in the least common multiple. Between the separate factorization, 3 occurs greatest in which one? Not this one. There are no 3s. It occurs greatest one time in this factorization. You need 1 3. 12 is your least common multiple. So, ladies and gentlemen, I've taken a lot of valuable time to show you 2 different ways of finding a least common multiple of 2 numbers. I've shown you this repeated division by prime method. And then I've shown you another technique called the prime factorization method. Both methods work. Take your pick, which method you like the best. Maybe you don't like any of those methods. Maybe you're gifted enough, ladies and gentlemen, to just look at these numbers 4 and 6 and determine, bing, in your mind that 12 is the least common multiple. And if you are, that's just more power to you. All right, so we determined the least common multiple is 12. Now we're not done. The next step is to build these fractions now up into equivalent fractions where both denominators have to become, what do you think? Both denominators have to become 12. So what do I multiply 1/4 by to build it up into an equivalent fraction with a denominator of 12? What are you going to multiply 4 by to build it up to 12?
3.
So you got to multiply the numerator by 3 also. So what's 1 times 3? 3.
3.
So 3/12 is equal to 1/4. 3/12 is another name for 1/4. In a similar way, how do I build 5 6 up into an equivalent fraction with the denominator of 12? What do you multiply 6 by to accomplish that?
2.
2. You got to multiply the numerator by 2 also then. What's 5 times 2? 10. So we say 10/12 is an equivalent fraction to 5 6. These are equal. Now that we have a common denominator, life is good. We add our numerators together, place the result over our common denominator. And ladies and gentlemen, it looks like our final sum of these 2 fractions would be 13/12, of which cannot be reduced. 13/12 is the sum of 1/4 and 5 6. Everybody see how that happened? And if you insist on putting this into a mixed number format, or maybe Alex requires that you do so, 12 divides into 13 one whole time with 1 out of 12 left over. Okay. Please don't fall into the trap of doing this. I seen this garbage too in the past too many times. And seeing this type of stuff, ladies and gentlemen, is one of the big reasons why I'm getting gray hair. I've seen students say, oh, it's easy to add fractions together. Just add the numerators together. Place that over the sum of the denominators. You know, ladies and gentlemen, if it was this easy to add fractions together, I would be out of a job. I'd have to do something else for a living. This is total hogwash, though. It's illegal. It's not true. It's not accurate. It doesn't work. Okay. You want to see why it doesn't work? I'll show you this. I'll show you one example that shows you why that's insane. 1/2 plus 1/2. Suppose that you said that this method is the way to go. Well, according to the method, it should be 1 plus 1 over 2 plus 2. Which, according to this method, should be what? 2 over 4. But doesn't 2 over 4 reduce right back down to 1/2? Now, are you going to tell me that if you eat 1/2 of a pizza and you eat the other half of the pizza, you've only consumed 1/2 of the pizza? Say what? If you ate one half of a pizza and ate the other half of the pizza, you only ate one half of the pizza? Makes absolutely no sense. Don't let that happen to you, okay? No, you got to get a common denominator. You have to build your fractions up into equivalent fractions and then go from there. All right, subtraction works the same way. So does adding mixed numbers together. Actually, when you add mixed numbers together, one way to do it is to turn these into improper fractions. So 2 1/2 would become what? 2 times 2 is 4 plus 1 is 5. So this would be 5 halves. Plus 3 1/4. 3 times 4 is 12 plus 1 is 13. This would be 13 fourths. Okay. Can anybody tell me what the least common denominator or least common multiple of 5 and 9 is? This is not as obvious as 4 and 6, but can you think of maybe what it might be? Or if not, we're going to have to use one of our techniques I showed you.
45.
All right, 45, you're saying. You're saying the least common denominator of 9 and 5 is 45. Like I said, if you can think of that, that's only going to speed things up. But, you know, I mean, suppose again, you know, you can't see it. Well, you're welcome to use one of my two methods I showed you. Repeated division by prime method. A prime number divides into 5 and or 9 would be 5. 5 divides into itself once, does not divide into 9. 3 is a prime number that divides into 9. 3 is a prime number that divides into 3. And we're done. Your least common multiple has got to be 5 times 3 times 3. Which is 45. You were right. Your least common denominator is 45. Okay. Or we could use the prime factorization method if you want to also. So we know the common denominator is what? 45. The next job is to build these fractions up into equivalent fractions that take on the denominator of 45. So what do I multiply the first fraction by? What do I multiply 9 by to build it up to 45?
5.
5. So we're going to have to multiply this first fraction by 5 over 5 to build it up into an equivalent fraction, which is going to be 20 over 45. Minus, what do you multiply 5 by to build it up to 45? You got to multiply 5 by what? Build it up to 45 by what? 9?
Yeah.
You got to multiply the numerator by 9. So what's 2 times 9? 18. So 18 45ths is equivalent to 2/5. Now we have a common denominator. Life is good. All we got to do is take 20 minus 18 and place that over 45. So what are we going to have? We're going to have 2 over what? 45? So 2 45ths is the difference between those two fractions. And notice this is a proper reduced fraction. That's your answer. All right. What did I have these as improper fractions? 2 1/2 I had as what? 5 halves?
Mhm.
And 3 1/4 I had it as what? 13 quarters or 13 fourths? What's the common denominator of 2 and 4?
4.
Or we got to build both these fractions up into equivalent fractions that have to take on the denominator of 4. The first fraction's denominator is 2. It has to be multiplied by 2. Which means you got to multiply the numerator by 2 also. So 5 halves times 2 over 2 becomes the equivalent fraction 10 fourths. 13 fourths already has the common denominator of 4. We need do nothing with it. Bring it along. Now it's just 10 plus 13, which is 23 over 4. And you could turn that back into a mixed number. 4 divides into 23 5 whole times with 3 out of 4 left over. That's one way in which to add those mixed numbers together. Everybody see that there? Everybody see how I added those mixed numbers together? I turned them into proper fractions first and then went from there. Okay. Is that the only way I could have added these mixed numbers together? The answer is absolutely not. I could have added them together by leaving them as mixed numbers, and I could have worked it in what's called vertical format. So, ladies and gentlemen, I'm going to show you another way in which you can add those mixed numbers together, 2 1/2 versus 3 1/4, and I'll let you decide what method you want to use. To add these mixed numbers together, you could have also worked vertically and left them as mixed numbers. It doesn't matter which one you put on the top or bottom. My least common denominator is still 4. I got to build this mixed number up into an equivalent mixed number where the denominator becomes 4. Likewise, I got to build this mixed number up into an equivalent mixed number where the denominator of the fraction must be 4. What do I multiply 1/2 by to build it up to a fraction with a denominator of 4? 5/5. So 2 and what? 5/4. What? We don't multiply by 5. What do we multiply by? What do I multiply 1/2 by to build it up to an equivalent fraction with a denominator of 4?
4.
What's that?
Was it 4?
Oh, not 4. 2 times 4 would be 8, correct? I just went under
Oh, my
2
bad.
times 2,
So-
right? Gives me 4. So all I gotta do is multiply 1/2 by 2/2 to build it up to an equivalent fraction, which is 2/4. There we go. Isn't that true? Let me make sure I'm doing the right problem here. 2 and 1/2 plus 3 and 1/4. Yes, I am. Okay. All right. Now, what do I multiply 4 by to build it up to 4? Well, 4 is already the common denominator. We don't have to do anything to this fraction. Now, what's 2/4 plus 1/4? And 2 plus 3 is what? 5. So we get 5 and what? 3/4. You know, the nice thing about adding these mixed numbers together like this by leaving them as mixed numbers is because our final answer is already a mixed number. If you turn these into improper fractions, like I demonstrated on the PowerPoint, and add them together, you have an improper fraction in the end of which has to be turned into a mixed number. So there's pros and cons with both methods. Okay. That's another way you can add mixed numbers together vertically like that. Leave them as mixed numbers and add them together. You still got to get a common denominator and equivalent fractions. Don't get me wrong. But it still works. All right. Okay, fractions and decimals. I have a true-false question for you. Any fraction or mixed number can be written as an equivalent decimal. True or false? What do you think? Any fraction or mixed number can be written as an equivalent decimal. True or false?
True.
That's true. That's always true. Yeah. And Liaison, we're going to try to maybe show you how to do a little bit of this, okay? First of all, we need to understand our places of our decimals. This is the decimal point. The decimal point is right here. That's the almighty decimal point. One place to the left of the decimal point is the ones place. 2 places to the left is the tens, then the hundreds, then the thousands place, then the 10,000s place, then the 100,000s place, then the millions place. What would be next after millions? Then the billions place. And then the 10 billions place, then the 100 billions place, then the trillions place, then the 10 trillions place, then the 100 trillions place, et cetera, et cetera. One place to the right of the decimal point is called the tenths, not the tens. Notice this is called the tens. This is the tenths, the THS ending, totally different. This is the tenths place. 2 places to the right of the decimal point is not called the hundreds place, it's called the hundredths place, THS ending. 3 places to the right of the decimal point is not the thousands, but the thousandths place. Then the 10,000ths place, then the 100,000ths place, then the millionths place, then the 10 millionths place, then the 100 millionths place, then the billions place, then the 10 billions place, the 100 billions place, the trillions place, 10 trillions place, 100 trillions place, et cetera, et cetera, et cetera. Got to know the names of these places to the right and the left of the decimal point. All right, ladies and gentlemen, we're going to try to show you how to write 5/8 as an equivalent decimal. How do you think we're going to do it? Well, we're literally going to divide the denominator into the numerator. This fraction bar means division. So how many times does 8 divide into 5? Well, it doesn't. It divides in 0 times. Okay. So we view this as being 50 then. How many times is 8 divided into 50? Oh, by the way, bring the decimal point up into your quotient. Establish its home before you divide. Always establish the location of the decimal point first before you divide. Now, 8 divides into 50 how many times? 6 times. 6 times 8 is 48. Subtract 48 from 50, you get 2. Bring down the next 0. 8 divides into 20 2 times. 2 times 8 is 16. Subtract 20 minus 16 is 4. Bring down the next 0. 8 divides into 40 finally, 5 times. And finally we get what? A 0 remainder. That means our decimal has terminated. Okay. So ladies and gentlemen, the decimal equivalent form of 5/8 is equal to 0.625 or 625 thousandths. We read this as 625 thousandths. The 6 is in the tenths place, the 2 is in the hundredths place, the 5 is in the thousandths place. 625 over 1,000. What do you think 625 over 1,000 would reduce back down to? Anybody? What do you think that's going to reduce that back down to?
5/8.
5/8 equivalent. So 5/8 is equal to 625 over 1,000, or as a decimal, 5/8 is equal to 625 thousandths, 0.625. We call this a what kind of a decimal? Ladies and gentlemen, that is called a terminating decimal. Terminating decimal. Because the decimal point terminates after the 5. Well, look at that. Wouldn't you believe they put a period at the end of the sentence and that period looks like a decimal point? That should not be there. That's not a decimal point. The decimal point's right here in front of the 6. 0.625. We call this a terminating decimal because to the right of the 5 would be nothing but zeros. We basically just call that termination of the decimal point. Do you think all decimals terminate?
No.
Nope. This one did. But not always is that true that a fraction has a terminating decimal. We call this a terminating decimal. All right, here we go. 5/6. Let's try to write the decimal equivalent form of 5/6. We do that by dividing 6 literally into 5. 6 divides into 5 0 times. Oh, by the way, make sure you establish the location of your decimal and the quotient, your answer. Bring it up immediately first before you do any division. All right, 6 divides into 5 0 times. 6 divides into 50. View this as 50 then. 6 divides into 50 8 times. 8 times 6 is 48. Subtract 48 from 50, you get 20. 6 divides in, oh, we got to bring down to 0 then. 50 minus 48 is 2, bring down to 0. 6 divides into 20 3 times. 3 times 6 is 18. 20 minus 18 is 2. Bring down the extra 0. We keep dividing. We keep dividing until one of two things happens. Either we see a termination in the decimal point, we get a 0 remainder, or we see a repeating nature of the decimal. 6 divides into 20 3 times. 3 times 6 is 18. Subtract 18 from 20, we get 2, bring down to 0, we get 20 again. I'm sensing deja vu. Ladies and gentlemen, what's going on here?
Keep repeating.
That's right. This 3 is going to repeat till the end of time or death, whatever grabs us first. This is called a repeating decimal. It's the decimal equivalent form of 5/6. 0.833333333. That repeats forever. That's equal to 5/6. To indicate the repeating nature of the 3, we put a bar above the 3. That bar means a 3 repeats forever. That makes sense. Repeating decimal. I'll let you in on a little secret, ladies and gentlemen. Another definition for a rational number. I'm going to write it out, spell it out for you. This is another alternative definition for a rational number. One way to say we have a rational number is to say that if the number can be expressed as a fraction, it's a rational number. Here's another definition. A rational number is any number whose decimal either terminates or repeats. There's an alternative definition for a rational number. Any number whose decimal either terminates or repeats is called a rational number. 5/6 is a rational number because not only is it expressed as a fraction, but we see its decimal it repeats. Okay, it's a repeating decimal. Back here, 5/8 was a rational number, not only because it's expressed as a fraction 5/8, but because, ladies and gentlemen, its decimal terminates. So any decimal that terminates or repeats is a representation of a rational number. All right. Here's a decimal that repeats 0.6262626262626262 to go on forever. To represent that, you put a bar above the repeating digits, 6 and a 2. Okay. Now, any terminating decimal can be written as a fraction from using the procedure on the next slide here. So if we have a terminating decimal, we drop the decimal point, place the resultant number in the numerator of a fraction. We use a denominator of 10 if there was 1 digit to the right of the decimal point, a denominator of 100 if there were 2 digits to the right of the decimal point, a denominator of 1,000 if there were 3 digits to the right of the decimal point, and so on. Step 3, reduce the fraction if possible. So 0.8. Drop the decimal point and put 8 in the numerator. What's my denominator going to be? Now, based on what we've seen in the previous screen, there is only 1 digit to the right of the decimal point, so this would be over 10. But I got an even easier way to understand how to write the denominator. How do we read this number, ladies and gentlemen? We don't read it as 0.8. We read it as 8 what? What place is the 8 in? Do we remember the names of the digits to the right of the decimal point?
Is it in the hundred?
No, not the hundreds.
Tenth.
The tenths place.
Oh.
We read this as 8/10. Now listen to what you just said. 8/10. Isn't 8/10 8/10? That's what it means to say 8/10, 8/10. That's why we write it as 8/10, because that's how we read the decimal. Now this can be reduced, right? 8/10. And can this be reduced? Well, yeah. By what?
So,
We can take this down by 2. Take it all the way down to 4/5. Do you agree? 4/5 is equivalent to 8/10 or 8/10. Equal. All right, help me read this decimal. How do I read it? 65 what? What place is the 5 in? The 6 is in the tenths place.
Hundredths.
The 5 is in the hundredths place. So we would read this as 65 hundredths. We would literally put 65 over 100. Or if you're not into it this way, on the previous slide, remember it says you drop your decimal point, put the number in the numerator, and then since there's 2 digits to the right of the decimal point, we put in the denominator 100. There's only 1 digit to the right of the decimal point, we put only 10. So either way you do it, ladies and gentlemen, hopefully we get it right, have 65 over 100. And of course, 65 over 100 would reduce down by 5, down to 13/20. Is that correct? If I reduce 65 over 100 by 5/5?
Yep.
How do we read this decimal? Or suppose we want to follow the previous slide on the PowerPoint. Well, we drop the decimal point and put 24 in the numerator. How many digits to the right are to the right of the decimal point here? 3. So I would place this over what? 1,000. There you go. Or maybe you can do it by this reasoning. How do you read this decimal? 24 what? What place is the 4 in? Tenths? Hundredths? Thousands place. This is 24 thousandths. That's why we write it as 24 over 1,000. And of course, that could reduce down. Can you think of how to reduce this? Well, we could at least start pecking away at it with 2. 2 divides into 24 12 times, divides into 1,000 500 times. 2 divides into this again. So 2 divides into 12 6 times, divides into 500 250 times. Yes, it reduces down by 2 again. 2 divides into 6 3 times, divides into 100, 250, 125 times. And ladies and gentlemen, I don't think we can go any lower than that. That's in the reduced form. Okay. All right. How do we read this mixed number? 2 and 65 what? 2 and 65 over
100.
100. 2 and 65 hundredths. So we write it the way we read it. Or if you're not into that, you got to realize you got 2 whole parts. And then the fractional part, you drop the decimal point 65 over, since you got 2 digits to the right of decimal point, 65 over 100. Can we reduce 65 over 100? Well, by 5, 65 reduces down to what? 13, and 100 divided by 5 takes it down to what? 20? And that would be equivalent to that next number. Do we understand how we're writing decimals, terminating decimals as equivalent fractions?
Yes.
Okay, let's move onward now. I gotta erase this. Okay. Ladies and gentlemen, can we write a repeating decimal as a fraction? The answer is yes. It's a little bit more strange, but it can be done. Step 1, write n equals the repeating decimal. Right? N equals the repeating decimal, and multiply both sides of that equation by 10 if 1 digit repeats, by 100 if 2 digits repeat, etc. Oh, interesting. Step 2, now you will have 2 equations. Subtract the first equation from the second equation. The repeating part of the decimal will subtract away. Divide both sides of the resulting equation by the number in front of n. This will be the fractional equivalent to repeating decimal. Reduce if necessary. All right. I see it. I read it. But do I really understand it? Well, examples are the only way to breathe life into that. All right, let's try to change 0.888888888888 repeats forever to an equivalent fraction. Ladies and gentlemen, it is a repeating decimal, so it should be represented as, it should be representable as a fraction because it's a rational number. Remember, I said a rational number is a decimal that either repeats or terminates. All right, now what is all this? What is this business up here? It says, write n equals the repeating decimal and we multiply both sides of that equation by 10 if 1 digit repeats, by 100 if 2 digits repeat. Write n equal to the repeating decimal. Write n as the repeat. I'll tell you what, I'm not going to try this because your author has done this for us. Here we go. Write n as the repeating decimal, 0.88888. Multiply both sides of this equation by 10. Why only by 10, not by 100 or 1,000 or whatever? Why only by 10? Because of how many digits repeat? Only one digit repeats. Because only 1 digit repeats, we multiply by 100, by 10. If 2 digits repeated, we multiply both sides by 100. If 3 digits repeated, we multiply both sides of our equation by 1,000. So we multiply both sides of this equation by 10 only. And we multiply the right side by 10, the decimal point gets shifted 1 place to the right as 8.88888888. Now it says subtract the first equation from the second equation. So we take this first equation, which is n equal to 0.888888888, and subtract it from the second equation after having multiplied both sides of the first equation by 10. What's 10n subtract 1n? 9n. Now what's 8.8888888888888888 minus 0.88888888888? What happens all the digits to the right of the decimal point?
Repeats.
Well, no,
Okay.
when you subtract them, what happens?
Cancels out.
They're all gone. I mean, they are all wiped away to infinity. Do you agree? And we're left with just 8. And finally, ladies and gentlemen, to solve for n, we divide both sides by what? 9.
Mhm.
And lo and behold, you have the fractional equivalent form of 0.88888888888. It's 8 9ths. See that there? How they did that? You take a calculator and divide 8 by 9. What's your calculator going to show? What had it better show? 8 divided by 9 better be equal to that what? 0.8888888, correct? Repeating decimal. Convince yourself, take your calculator, divide 8 by 9. It better be the repeating decimal 0.888.
It is.
It works, doesn't it? It's a technique that works. I need a little practice on that one. And I'm just trying another one here. How many digits repeat here?
2.
2.
2. So first of all, I'm going to write n equals 0.63, 0.63, 63, 63, 63, 63, 63. We write n equal to this. Then I multiply both sides by what? 10 or 100? How many digits repeat here?
2.
2. So
2.
I got to multiply both sides, not by 10, but by
100.
100.
by 100. You got to multiply both sides by 100. You got to multiply the right side by 100 also. Then you're going to be left with 100n is equal to what? What happens to the decimal point when you multiply it by 100? It gets shifted not one, but what? 2 places to the right?
2 places.
So this is going to be 63 point what? 0.63, 63, 63, 63, 63, correct? True?
Yep.
Now we're going to take the first equation and subtract it from what? This equation. That means we subtract off our first equation, which was n equal to what? 0.63, 63, 63, 63, 63. And we subtract. What's 100n minus 1n?
99n.
99n. Now what happens to the decimal portion here? When you subtract off the 0.636363 forever, all this is wiped away. Do you agree?
Yes.
And we're left with 63. Now we simply divide both sides by what? 99, and you got it. Ladies and gentlemen, 0.63, 63, 63, 63, 63 is really 63 over 99. That's the decimal equivalent form of that repeating decimal right there. Okay, see how we're doing this here? Now, my writing's a mess, but there's good news because it's all explained on the following PowerPoint slide right there. It's all explained. Everybody see how we're doing this here, Lizzo?
Yes.
How to write a repeating decimal as an equivalent fraction. Okay. Notice they reduced that fraction down too. Interesting. All right. You know, do you think there's word problems that have fractions in them ever? Yes, there are. In her final 2 days of preparation for a triathlon, Kat hopes to swim, run, bike a total of 50 miles. She works out at the nearby state park with a swimming quarry and running biking trail. One lap in the quarry is 1/4 of the trail. Wait a minute. One lap in the quarry is 1/4 mile. And the trail is 3 1/4 miles. The first day, Kat swims 6 laps, runs the trail twice, and bikes it 5 times. How many more miles does she need to cover the second day? Oh. How many times does how many laps she swim? 6 laps? And each lap is how long? So there's she swam 6 laps. Each lap is 1/4 mile long. This would be the total number of miles that she swam on day 1. Plus, oh, but wait a minute. We got the other thing, namely the running and the trail twice. She went down, she runs the trail twice. She runs the trail twice and bikes it 5 times. The trail is 3 1/4 miles long. So if she runs this trail twice, that means the total distance she covered would be 2 times 3 1/4 miles. That's the total mileage that she covered when she ran the trail twice. Plus, but she biked the trail 5 times, and each time she covered 3 1/4 miles. So if she biked it 5 times, the total distance she covered would be 5 times 3 1/4 miles. We got to add all these up, and that would be the total mileage that she covered on day 1. We got to work this all out. And then we're going to subtract this total mileage from 50 miles, which is her objective, to determine how many more miles she has to run or cover during the second day. That's how we're going to have to do this problem. So first we gotta add all these things up. You know, I bet dollars to donuts, they did this on the next slide. Let's go down. There it is. This is the total number of times she swam, the number of miles from swimming, total number of miles from biking, total number of miles from, wait a minute, this is the total number of miles from running, excuse me, total number of miles from biking. The mixed number for 3 1/4 is 13/4. So they turn the mixed numbers into improper fractions. And what's 6/1 times 1/4 plus 2/1 times 13/4 plus 5 times 13/4? Ladies and gentlemen, what's 6/1 times 1/4? 6/4. What's 2 times 13/4? 26/4. What's 5 times 13/4? 65/4. At least we have a common denominator. We add the numerators together and we get 97/4. During day one, she covered 97/4 miles. That's about as clear as mud in my mind what that's saying. We might want to convert this back into a mixed number so we can appreciate or fathom the distance covered during the first day. How many times? All right, that's 97/4 miles. So in order to determine how many more miles she has to cover during day two, we have to take 97/4 miles and subtract it off from her objective, which is 50 miles. What's 50 or 50/1? Subtract 97/4. They did not convert 97/4 into a mixed number. Nonetheless, we need a common denominator of 1 and 4, which would be 4. They built 50/1 up into an equivalent fraction of 200/4 by multiplying it by 4/4. Now, what's 200/4 minus 97/4? That's 103/4. Now they convert it to a mixed number so that we can better fathom or interpret how many miles she has left remaining on day two. 4 divides into 103 25 times with 3/4 left over. Ladies and gentlemen, on day two, she has to cover 25 3/4 miles to fulfill her 50-mile quota or objective. Okay? That's a long problem, but did it make any sense as to what they did to accomplish the answer? The good news is it's all on the PowerPoint here. And you can mull over it at your own leisure, okay? All right, so that's the end of that. We don't have much time, unfortunately, but I wanted to see if we could maybe do a couple problems here. This is section 5.3. The key, ladies and gentlemen, is practice, practice, and more practice. Even if it means going in your textbook and doing more practice, maybe with the odd problems and checking your answers. Or I will post some supplemental practice with all these operations involving fractions and mixed numbers. Please do the extra practice and check your answers. That coupled with ALEKS practice, hopefully will get you ready for any sort of quiz or exam. Okay, but it's only going to come through a lot of practice. Only through a lot of practice. You got to roll your sleeves up and spend time with this. And if you do, good things start to happen. If you don't, bad things happen. All right. Can you reduce fractions here? All right. I'm assuming we're okay on this. Now, some of these numbers are getting big, in which case you're going to need your calculator to help you out to try to come up with, some sort of a divisor. Or you're welcome to break these numerators and denominators down into prime factored form and go from there to reduce. You can always do that. Here they're having you build fractions up into equivalent fractions. All right, equivalent fractions. For instance, ladies and gentlemen, number 29, 19/24 would build up to what fraction over 48? Go ahead and do this. We'll call this classwork number 2. Number 29, 19/24 becomes what over 48? Go ahead and do that quickly. Classwork 2. We'll open up a running tab on classwork 2, number 29. What is it? 19/24 is equal to what over 48? (48) divided by 24 is 2. That means they multiplied 24 by 2 to build it up to 48, which means you got to multiply your numerator by 2. What's 19 times 2?
38.
38/48 is equivalent to 19/24. 38/48 is another name for 19/24, equivalent fractions. All right, that one's good. Ladies and gentlemen, I want you to try this problem, number 39, part of classwork 2. I want you to add these, well, actually subtract these fractions. A negative 11/12 minus 5/8. You have to get a common denominator and go from there. Try to do that problem, classwork 2. Anybody get the common denominator?
24.
24 works great. Hey, if I used 48, would I be in trouble? If I use 48 for my common denominator, would that be a problem? No. 48,
You just have more simplifying to do.
48 is divisible by 8 and 12. There's an infinite number of common multiples of 8 and 12, ladies and gentlemen. But if you want to minimize the amount of reducing you got to do in the end, you might want to choose the least common denominator, the smallest one. All right. So both these fractions now got to be built up into what? Equivalent fractions that take on the denominator of 24. 12 times 2 is 24. You're going to multiply 11 by 2 to build it up to 22. So therefore, negative 22/24 is equivalent to negative 11/12. 8 must be multiplied by 3 to build it up to 24. Got to multiply the numerator by 3. So 15/24 is equal to 5/8. Now remember I said it doesn't matter where you attach the negative signs? Remember I indicated that, ladies and gentlemen?
Who did?
I'm going to attach it to the numerator. So I got negative 22 minus 15. And that's all going to sit over what? What do you think I'm going to put that over?
24.
Common denominator.
24.
What's negative 22 minus 15? Well, that's negative 22 plus a negative 15. A negative plus a negative is a negative, and we add. So that's going to be negative what? 37?
37, yeah.
Over what? 24. Can I reduce this? No. In fact, I think 37 is what kind of a number? What kind of a number is 37? It is a
Prime number.
prime number. Yeah, it's a prime number. Your answer's got to be negative 37/24. And again, in your answer, it doesn't matter where you put the negative sign. Let's see where they put it. They put it outside, negative 37/24, or they even converted a mixed number into negative 1 and 13/24. All right. All right, let's see what else. Running out of time, as always. Ladies and gentlemen, do you think the order of operations could ever have problems involving fractions or decimals?
Yeah.
Is yes. What would I do first with 45? Where would I begin the action with 45?
Parentheses.
Inside the parentheses. So I'm going to divide 7/16 by 3/8. How do we do that? Well, we change division to
Multiplication.
and do what to the second fraction?
Reciprocate.
Flip it upside down, take its reciprocal. And this is the resultant equivalent problem we're up against now. Still inside the parentheses, do I need a common denominator? The answer is no. Can I do any cross canceling later on between the 3 and the 7? No, but between the 8 and the 16, yes. 8 divides into itself once. 8 divides into 16 2 times. I'm left with 7 times 1 over 2 times 3, 7 6 times the 8/5. Can I do any cross canceling here because we're running out of time?
I think it's 3/5.
Yeah, look. 2 divides into 6 3 times. 2 divides into 8 4 times. That's valid cross canceling. We're left with 7 times 4, which is 28 over 3 times 5 is what? 15. That cannot be reduced. Now you could turn that into a mixed number if you desire to do so. It would be 1 and what? 13/15. You got your answer. So yes, ladies and gentlemen, the order of operations are still in effect. It doesn't matter if you have fractions, nothing changes. PEMDAS, please excuse my dear Aunt Sally, is still in effect. Okay. Nothing changes. The only thing that changes is the type of numbers you're working with. All right. So, they got a whole bunch of, order of operation problems to really strengthen your ability to work with fractions. Now, I don't have much time left, but I am going to work number 58 out on my paper in detail because this is probably one of the more difficult ones. And if you can do a difficult problem, then the easier ones should seem like a piece of cake. Okay. So I'm going to work out this nasty problem number 58 here on my paper. We're down to about 19 minutes past the hour. So if you have to split, ladies and gentlemen, by all means go. This will be on the recorded video. But if you want to hang around, if you have any questions, I'll be done with this pretty soon. It won't take that long. The key is you got to relax and you have to remember your order of operations and you begin to chip away at it one little step at a time. You don't try to do this all at once. It's too much. All right, where does the action begin? I got parentheses. I begin inside the parentheses right in here. I need a common denominator of 3 and 4 because I'm asked to add these fractions together. What is my least common multiple of 3 and 4? After a little thought or using one of my methods I showed you, you come up with 12. Now I got to build these fractions up into equivalent fractions where both the denominators become what? 12. All right, so what do I multiply 2/3 by to build it up to something over 12? By 4 over 4. So 2/3 becomes what? 8/12. 3/4 must get multiplied by 3 over 3 to build it up to an equivalent fraction of 9/12. I'm going to do the same thing here. I got to subtract some fractions. I need a common denominator of 8 and 16, which after a little thought, or one of my methods, you would have 16. 9/16 already has the least common denominator, just bring it on down. 1/8 must be built up to an equivalent fraction with a denominator of 16 by multiplying it by 2 over 2 to build it up to 2/16. Still inside the fraction, inside the parentheses. What's 8/12 plus 9/12? 8 plus 9 is 17, so this is 17/12. Still inside the parentheses. What's 9/16 minus 2/16? 7/16. We're done inside the parentheses. Ladies and gentlemen, what do I do next? Do I multiply, deal with exponents, or add? Order of operations.
It would be the exponent.
Exponents. Unfortunately, oh my gosh. Are you kidding me? We got to do 17/12 times itself 3 times. Nasty, nasty business here. Well, that's what's called for. So calculator, here we go. That's going to be 4,900 and what? $13 over what's 12 cubed? 1728. I'm probably not going to give you a problem this strenuous for a quiz or an exam, ladies and gentlemen. Maybe for a homework problem, but that's it. This one, we're going to need a little help from an electronic device. Now, 7/8 gets multiplied by 7/16. Now, a negative times a positive is a multiplication. Negative times a positive is a negative. And you know what? Unfortunately, 2 does not divide into 49/13 because it's not an even number. Last digit's not even. So we're going to have negative 4,913 divided by 2 times the 1728. What is 1728 times 2? 3,456. 7/8 times 7/10. There's no cross canceling available either way. So 7 times 7 is 49. And 8 times 10 is 80. Now we're being asked to add these add these fractions together. Holy baloney. Unfortunately, 80 does not divide into 3456 evenly. So we can't use 3456 as the least common multiple. Okay. Now, like I said, these numbers are kind of big here. Now, you know, finding the least common multiple of this guy is going to be kind of nasty because we got a big old number there at 3456. And, you know, it could be done. I'm gonna use my repeated division by prime method here. Prime number that divides in at least one of these numbers would be 2. It does divide into 30. Oh, this is 3456. 2 does divide into 3456, 1728 times. Will divide into 80 40 times. A prime number that divides in at least one of these numbers again would be 2. 2 divides into 1728 864 times. And divides into 40 20 times. You can't use 4. Why can I not use 4 out here? Because 4 is not a what? Prime number. It's got to be a prime number. 2 works again. 2 divides into 864. How many times? 432. Divides into 20 10 times. 2 works again. Divides into 432. How many times? 216 divides into 10 5 times. 2 works again, divides into 216. 108 times. Divides into 5? No. Okay, let's see what else we got here. 108 divided by 7. Oh, well, 2 will work again. It divides in there 54 times, does not divide into 5. Let's see, what divides into 54? 3 divides into 54. I think, right? No, it doesn't. Yeah, it does. 18 times. Okay. And 3 does not divide into 5. 3 divides into 18 6 times, does not divide into 5. 3 divides into 6 2 times, does not divide into 5. 2 divides into 2, does not divide into 5. This is a 1. And then 5 divides into 5, and we're finally done. All right, so 2 times 2 times 2 times 2 times 2 times 2 times 3 times 3 times 3 times 2 times 5. How many 2s? 1, 2, 3, 4, 5, 6, 7. So the least common denominator is going to be 2 to the 7th power times 1, 2, 3, 3 to the 3rd power times a lonely 5. Big number. So 2 to the 7th power times 3 to the 3rd power times 5 is going to be 17,280. So therefore, both of these denominators have to be built up to 17,280. Now, 17,280 divided by the 3456 suggests we multiply top and bottom of this fraction by 5. So 5 times 4913 is going to be 24,565. 80, when you take 17,280 divided by 80, that gives you 216. So you get multiply top and bottom of this fraction by 216. 216 times 49 is 10,584. Finally, you have a negative plus a positive all over your common denominator. Nasty, horrendously large numbers, but nonetheless, the process is being illustrated. Negative 24,565 plus 10,584 gives me negative 13,981 over 17,280. Okay. And as far as reducing that is concerned, I'll let you think about that, but I don't know. I mean, nothing looks obvious as we can reduce. Nothing jumps out at me right away, but maybe you can try a little trial and error on your calculator. But nonetheless, ladies and gentlemen, that's a nasty problem. I'm never going to give you one this involved on an exam. I think that's a ridiculous problem, even with a calculator. Okay, but nonetheless, that illustrates the process. All right, so I'll stay on the line for a couple minutes if you have any questions.